In this lecture, we'll begin building portfolios of multiple assets and making decisions as to how to optimally allocate resources among those assets. Fundamentally, in economics, we think of individuals and investors as wanting to maximize their personal utility. So we're going to suppose in this course that all investors have an identical utility function, and that this utility function is a function of two variables, mu and sigma, where mu enters positively or increases the utility, and sigma enters negatively, that is, it decreases the utility as sigma increases, and that there's one parameter, gamma, which I'll describe in a few moments. Now, mu and sigma we are going to interpret as the mean of returns and the volatility of returns, respectively. Now, we can ask ourselves, what is the utility of holding the risk-free asset, the risk-free paying a mean mu sub f and having a volatility sigma sub f? Well, we know from the previous lecture that the expected value of the risk-free asset is in fact, which is by definition mu sub f, that is equal to r sub f because there's no variability. Specifically, sigma sub f is equal to 0. So if we plug in 0 into the utility function, and mu sub f being r sub f, then the result we get is the utility is simply equal to r sub f. Now, for a risky portfolio where sigma is not 0, the utility can be thought of as a certainty equivalent return. So we can still think of this utility as a return. In particular, it's the return that a risk-free asset would have to offer to provide the same level of utility as the risky asset. That is, this same value, there's an alternate value called u of r star sub f 0, such that r star generates the same utility as the risky portfolio with mu and sigma. And in that sense, it is a certainty equivalent return. That is, the risky portfolio offers the same utility as a risk-free asset with return r star sub f. Now, the parameter gamma is a measure of risk preference. When gamma is greater than 0, we say that individuals are risk averse, because in this case, volatility detracts from utility. If you recall, the utility looks like u of mu sigma equals mu minus gamma, well, there's a 1/2 here, sigma squared. Disregard the 1/2, we don't need to worry about that. You can see that if gamma is positive, sigma enters negatively, which means volatility is a bad thing, which means an agent with a positive gamma is risk averse, does not like volatility. Now, if gamma equals 0, we say that individuals are risk neutral. In this case, volatility does not enter the utility function at all. And investors then rank portfolios simply by their expected return. That is, when gamma is 0, u of mu sigma is just equal to mu. That's all. So only mean returns, that is, expected returns, matter. Sigma does not. If gamma is less than 0, well, there's a double negative sign. That is, u equals to mu minus gamma, which is now a negative number, could be interpreted as plus a positive number times sigma squared. In that case, volatility is entering the utility function positively, and that means that investors are risk loving. and so that they want to take on risk. So we'll generally assume in this course that investors are risk averse, and that the magnitude of gamma will dictate the amount of risk aversion. When gamma is very large, so we'll say that gamma is a positive number, and when it's large, that will mean that investors are more risk averse, because a small increment in volatility, in sigma, will take away more from the utility function when gamma is large. Now, under this utility model, it's pretty clear that investors prefer both higher expected return and lower volatility. So if we say that portfolio A has mean mu sub A and volatility sigma sub A, and similarly that there's a portfolio B with some mean mu sub B and volatility sigma sub B, then if the expected return of A is greater than the expected return of B, and if the volatility of A is lower than that of B, then A must be preferred to B. That is, you're not only getting more expected return, but you have less variability in the portfolio of A. So A strictly dominates B as a portfolio. You would never want to choose B over A. Now this picture depicts the trade-off between volatility and expected return. So plotting values of volatility on the x-axis, that is sigma on the x-axis, and expected return on the y-axis, we begin with some portfolio P that has expected return mu sub P and volatility sigma sub P. Now, as we just argued, any portfolio that has an expected return that is greater than the expected return to P and a smaller volatility than the volatility of P will be strictly preferred. That is, anything in this quadrant 1, any portfolio in this region has both a higher expected return and a smaller volatility, and hence is strictly preferred to the portfolio P. On the other hand, any portfolio in this quadrant 4, has both a lower expected return than P and a higher volatility. And those are both undesirable characteristics. So portfolio P is strictly preferred to any portfolio in quadrant 4. Now what about quadrants 2 and 3? Well, it turns out there's some ambiguity. Let's suppose that there's some portfolio Q that has a different mean and volatility than the portfolio P, but that portfolio Q yields the same level of utility as P. Then one of two things must occur. If Q has a higher mean than P, then sigma must also be greater. That is, let's begin with the assumption that Q has a higher expected return. If this were not true, that is, let's suppose that sigma Q is equal to sigma P, and that this is true, that the mean return is greater, then you would strictly prefer Q, because it has the same volatility as portfolio P and yet a higher expected return. In that case, portfolio Q must yield a higher utility. Likewise, if the volatility were less, that is, if sigma Q were less than sigma P, you would still strictly prefer portfolio Q because it offers a higher return and a lower volatility. And so, if we know that it yields the same utility as P, and if this is true, then it must be the case that that is true. Otherwise, it would yield a higher level of utility. And then we can flip the analysis. If it offers the same level of utility and it's offering a lower expected return, then by the same token it must be offering a lower volatility in order to increase the utility up to that of P. That is, the lower mean return decreases utility, and so to compensate, the volatility must also be lower. So what that means is that Q must lie in quadrants 2 or 3. If we recall that diagram with P at the axis, quadrant 1 being here, quadrant 4 being here, we know that anything in quadrant 1 is strictly preferred to portfolio P here. Anything in quadrant 4 is strictly dominated by portfolio P. Then portfolio Q must lie somewhere in quadrants 2 or 3. If we map out all portfolios like Q that yield the same utility as P, that would constitute an indifference curve. We conclude that indifference curves then must cut through quadrants 2 and 3, because any portfolio like Q that yields the same utility as P must be, by our arguments, in quadrants 2 or 3. So the picture looks like this. With P here, we know that any portfolio in quadrant 1 is strictly preferred to P. Any portfolio in quadrant 4 is strictly dominated by P. And that any portfolio that yields the same utility must be somewhere in these two quadrants through here. And this blue line happens to map out, according to the utility function, what those points are that yield the exact same level of utility. Now suppose an individual can invest in two different assets. One is a risky portfolio that we'll call P, and the other is the risk-free asset that we'll call F. The Greek letter omega will denote the fraction of wealth that the investor invests in P. And then 1 minus omega will be the fraction of wealth that the individual invests in the risk-free asset F. As we build portfolios in the lectures to come, we're typically going to assume that portfolio weights sum to 1. And this can be seen in what we've just done. We say some fraction of the investor's wealth is going into portfolio P, and then all the remainder, 1 minus omega, will go into the risk-free. Now, R sub P will denote the return to the risky portfolio P, and mu sub P is then going to be the expected return, and sigma squared sub P is going to be the variance of the return. Likewise, R sub F is going to denote the return to the risk-free asset. Mu sub F is going to be equal to the expected return, which is also just the return to the risk-free. So mu sub F is R sub F, and that's because sigma sub F is equal to 0. Now let C denote the complete portfolio of the two assets, where the individual has invested some fraction omega in portfolio P and some fraction 1 minus omega in portfolio F, or the risk-free. So C then is just a weighted average of P and F. That is, we will write C is equal to this fraction times P plus this fraction times F. It's very simple. The return to C then, the return to the whole portfolio, is simply the return to portfolio P weighted by omega plus the return to portfolio F weighted by 1 minus omega. So it's simply a weighted average of the two returns that the investor has put his or her money into. Now, by the linearity of expectations, by the properties that we've previously studied, the expected value of the portfolio C, which is mu sub C, well, that is equal to the expected value of R sub C. And now substituting this definition for R sub C, that is equal to the omega times the expected value of r sub p plus 1 minus omega times the expected value of r sub f, where what we've implicitly done here is taken the expectation around the whole thing first, and then by the properties of expectations, we've moved the expectation operator to each one of the terms and pulled the constants omega and 1 minus omega out. Well, we also know that the expected value of r sub f is simply r sub f. So in the next step, we simply substitute notation. Omega mu sub p, which is equal to the expected value of r sub p, and rf, which is just equal to the expected value of rf. Now finally, if we rearrange a couple of terms, how did we get from this step to this step? Well, what we did is we just distributed. We said omega mu sub p plus 1 minus omega r sub f is equal to omega mu sub p, and then distributing the rf plus rf minus omega rf, and then we can group this term and this term together as omega mu sub p minus rf, and then there's still this lone rf hanging outside, which is exactly how we got to that final equation. Now the term in parentheses, let's note, is the risk premium. That is, it's the expected value of portfolio P minus the risk-free rate, which is the expected return of the portfolio in excess of the risk-free rate, exactly what we defined the risk premium of portfolio P to be in the last lecture. And so this relation that we now have is the expected return to portfolio C is simply the risk-free rate plus some fraction times the risk premium. So the investor will earn the this risk premium in excess of the risk-free rate to the extent that he or she invests his or her wealth in the risky portfolio. Now, according to the properties of variance, if we want to compute the variance of the portfolio C, well, that's simply var of the return, R sub C, which is equal to, recall that's equal to var of omega R sub P plus 1 minus omega R sub F. Now, by the properties of variance, that is equal to the variance of each of the two terms with the coefficients pulled out and squared, which is what that term is and that term is, plus 2 times the constants and the covariance of the two random variables. Well, we know that RF is constant, and so the variance of RF should be 0, and also a constant should not covary with anything that's moving. So although RP, R sub P, is a random variable that has variance, RF is constant, and the covariance with R sub P should be 0. So that leaves us with only the first term remaining. That is, the variance of the portfolio C is simply omega squared times the variance of portfolio P, which we write as omega squared sigma P squared, substituting the notation sigma sub P for the variance of R sub P. So finally, if we take square roots of both sides, if we take square root of this side and square root of this side, we get a very simple formula. The volatility of portfolio C is simply omega times the volatility of portfolio P. Notice there is no contribution to the volatility of portfolio C from the risk-free asset. So if you recall from the equation, mu sub C is equal to RF plus omega times the risk premium to P. Well, if omega is 0, then this whole term goes away. That is, if the investor puts nothing into the risky portfolio P and instead puts 100% of her assets in the risk-free, then portfolio C is simply going to have expected return equal to RF. Likewise, in that case, sigma sub C, which is typically equal to omega sigma P, if omega is 0, that term also goes away, and sigma sub C is equal to 0. That is, the investor has simply created a risk-free asset by putting all of her wealth in the risk-free. Alternatively, if she put all of her wealth in the risky portfolio, then this equation right here, this part of the equation would not wipe away, but instead mu sub C would simply equal to RF, and now because she has put all of her wealth in, omega would be 1, and you would simply have mu sub P minus R sub F. These two terms would cancel each other out. That would simply be equal to mu sub P. Sigma sub C in this case, which is typically equal to omega sigma P, well, omega being 1 because she put all of her wealth in portfolio P, that would just equal sigma P. So when omega is 1, portfolio C is portfolio P because it has the same expected return and standard deviation. When omega is 0, portfolio C is the risk-free because it has the same mean return and the same standard deviation. Now in between those two extremes, when omega is small, investors are more risk averse, and so they expect a rate of return closer to the risk-free asset. Now less risk-averse investors, when omega is high, they expect a rate of return that's much closer to the risk premium of portfolio P, that risky portfolio. Likewise, for small omega, those investors that are risk-averse will have very small portfolio volatilities because, recall, sigma C, when omega is small, will have a very small right-hand side here. On the flip side, for less risk-averse investors, when omega is very high, they will have much higher portfolio volatilities. Now, since we have this relationship, this very convenient relationship that the volatility of the complete portfolio is simply omega times the volatility of the risky portfolio P, we can actually solve for omega. That is, omega is equal to sigma C over sigma P. In this case, then, we can take that relationship of mean returns that we derived on the previous slide, and we can substitute for omega right here. That is, the mean to portfolio C is equal to the risk-free rate times the ratio plus the ratio of volatilities multiplied by the risk premium. Well, if we group the risk premium and the volatility of portfolio P, then what we have is the Sharpe ratio. So that the mean return to portfolio C can actually be written, instead of writing it as omega times the risk premium, is actually the risk-free plus the Sharpe ratio times the volatility of C. It's just an alternate way of writing that same equation. Now this equation, the relationship between mu sub C, RF, and however we choose to write it, the risk premium, omega, we can either write it as omega or we can write it as the Sharpe ratio. Let's write it as the Sharpe ratio of portfolio P times sigma C. That is known as the capital allocation line. and it depicts a set of portfolios that are available to an investor. And so because this is a set of portfolios that's available to the investor, it's also a budget constraint. So in a moment, we're going to combine indifference curves with budget constraints, just like you did in your microeconomics course as a way of finding an optimal bundle of goods that an agent desires to consume. Well, in this case, we'll combine the capital allocation line, which is all the portfolios available to an investor, plus indifference curves to find an optimal portfolio. In this case, the capital allocation line then is plotting pairs of sigma and mu that the investor can choose. And really, the investor chooses them by selecting some omega. Recall that both mu sub c and sigma sub c are functions of omega. As I mentioned above, this is simply just a plot of the equation that we've derived previously. So this is the capital allocation line right here. Now, looking at that equation, clearly the intercept is going to be the risk-free rate, RF, and the slope is going to be the Sharpe ratio, because this sigma c is going to be the independent variable on the x-axis, mu sub c is going to be the dependent variable on the y-axis, then we have intercept and slope. So let's suppose that the risk-free rate is 7% per year, and that the mean return to some portfolio, that the expected return is 15% per year, that the volatility of that portfolio is 22% per year. Given that information, what is the capital allocation line? Well, we can compute the risk premium. Well, actually, we could compute the Sharpe ratio. First, the risk premium, the Sharpe ratio, is equal to the risk premium of portfolio P all over sigma P. The risk premium being mu sub P minus RF all over sigma P. Well, this is equal to 0.15 minus 0.07 all divided by 0.22, which is equal to 0.08 divided by 0.22. This is roughly equal to 0.36, which means then the capital allocation line, which is mu sub c, is equal to 0.07, the risk-free, plus the Sharpe ratio, which we've now derived as 0.36, times sigma sub c. That is the capital allocation line. So if you plug in some sigma sub c value, then I will tell you the corresponding mu sub c that you will have on the capital allocation line. The picture looks something like this. Here's the risk-free, which is the intercept. Here's some portfolio P. The slope then is the Sharpe ratio. It takes sigma sub P, and for every sigma sub P there's a rise that's equivalent to the risk premium. So in this numerical example, for 22% horizontal movement, there's an 8% rise, which is 8 over 22, which is exactly the Sharpe ratio. Then every point you give me a sigma, sigma could be right here, and I will tell you 0.07 plus 0.36, whatever that sigma is going to plot that value on the line, and that's what mu sub c is. Give me another sigma sub c, and I'll plug it into this equation right here, and it will give me the value on the line, which is mu sub c. Now, as I mentioned before, what individuals are really doing is seeking to maximize their utility subject to the available choice set. So in this case, we have a specification for a utility function. Agents are trying to maximize utility over the two choice variables, which are the mean return and the volatility. In particular, that maximization problem then looks like maximizing this function over mu and sigma. But that maximization problem is subject to two constraints. First, that mu sub c is equal to the capital allocation line. Well, that mu sub c is equal to RF plus omega times risk premium, and that sigma sub c is equal to omega times the volatility of portfolio P. What we can do is simply substitute those two constraints into the objective function, which was the utility function. So here we've substituted in for mu sub c, and here we've substituted in for sigma sub c, squared that is. And now, since we've substituted in the constraints, we can maximize this objective function in an unconstrained fashion. And now there's only one choice variable because we've substituted out for mu sub c and sigma sub c, which are both functions of omega. So given some value of mu sub p and RF and a value of gamma, we can then find the omega that maximizes the utility function. We do this by taking the derivative with respect to omega. That's actually not a very hard thing to do. Recall, if we actually do the work, we want to take the derivative with respect to omega of RF plus omega mu p minus RF minus 1/2 gamma omega squared sigma p squared. We're taking the derivative of that whole thing. Well, the first term, that derivative will be 0. The second term, that's just linear in omega. So we take, this is a constant multiplying omega, we're taking the derivative of omega, that drops out, and we're left with the risk premium. In the final term, we have a quadratic. The 2 comes down and it cancels the 1/2, and we set everything equal to 0. So what we have, so the derivative, setting it equal to 0, we have mu sub p minus RF is equal to, minus the 1/2 canceled with the 2 that came down off the omega. We have minus gamma omega. Omega is no longer squared because we took the derivative of omega squared. Sigma p squared is equal to 0. Well, what can we do? We can take this over to this side, so that what we really have is that mu sub p minus RF is equal to gamma omega sigma p squared, which is exactly what is written right here. And I've written omega star just to dictate that this is not just any omega, but it is the omega which sets the derivative here equal to 0. That is, it is the omega which maximizes that objective function. Now if we solve for omega, just by rearranging and doing some algebra, that is, we can take the gamma and the sigma p squared all over to this side into the denominator. We have omega star is equal to the risk premium divided by gamma sigma p squared. We recognize that the risk premium over sigma p squared, and now there's actually an error here, that is equal to the Sharpe ratio all over gamma sigma p. That is, this is because the Sharpe ratio is equal to the risk premium over sigma p. There's a sigma p squared in the denominator, so that's actually equal to 1 over gamma sigma p, where 1 sigma p and 2 sigma p's multiplied make the squared right there. And so in fact what we have is the Sharpe ratio over gamma sigma p. Now, as I mentioned before, the capital allocation line, that's simply a budget constraint. And so rather than performing this numerical optimization problem by computing a derivative like we just did on the previous slide, alternatively we can just plot a bunch of indifference curves and find one that's tangent to the capital allocation line. And the tangency is going to be the optimal portfolio. So to do this, we can start by fixing some utility value equal to r sub f. That is, whatever r sub f is, if r sub f is 0.7, then we're going to set our initial utility level at 0.07. We then recall the relationship that utility is equal to the mean of the portfolio C minus 1/2 gamma times the variance of portfolio C. And we can use this for whatever that mu bar is to solve for mu sub C. That is, simple algebra says you just take this latter part of the right-hand side and you just move it over, add it to the other side, so that mu sub C is equal to that utility level, whatever we started at, which is RF, plus 1/2 gamma times the variance of C. So we use this equation to find pairs of mu sub C and sigma sub C that correspond to that utility level. That is, if we simply use this equation right here, begin with a whole, just pick 100 different values for sigma C, plug it and start with some value for mu bar. Then for each value of sigma C you plug into this equation, you will get a mu sub C that corresponds to that utility u bar. And that's a way that you can plot out an indifference curve. That is, you begin with some utility target, you then solve for one of the variables in terms of utility and the other variable, and then you compute for a given set of inputs what the other variable would be. So you have two variables. For a given first variable, what is the second variable that corresponds to that utility? Now, what's the probability that that indifference curve that started at that utility actually is tangent to the capital allocation line? It's actually very low. So what you can do is, once you've plotted that indifference curve, pick a new level of utility which is higher and plot the next indifference curve. And if that still is not tangent, pick another utility level which is still higher and plot that indifference curve, and repeat until you finally find a tangency. So numerically speaking, we can set u equal to 0.07, and then we can start sigma. We can pick a whole range of sigma values here, and for each sigma, that equation that we had on the previous slide will give us a mu. And then these are the pairs of mu's and sigmas that fall on the same indifference curve by definition, because we fixed utility at that value. Alternatively, we can fix utility at this value, and then the equation will be slightly different because there will be a 0.078 in it instead of a 0.07, and so we'll get different mu sub c's on that indifference curve, and then this sigma corresponds to that mu for that indifference curve, this sigma corresponds to that mu for that indifference curve, and so on. We can repeat that process for many different utility values until we finally find one that's tangent to the capital allocation line. Graphically, we start with an indifference curve that runs right through here that has the same intercept as RF. That's what we're doing when we set U bar equal to RF. We're picking that indifference curve, which is necessarily going to undercut the capital allocation line. So we know when we set U bar equal to RF, we know that we're going to end up with an indifference curve that undercuts the capital allocation line because both of them must hit the axis right there. And then we can increase these utility values until we finally find the indifference curve that hits tangent right here, and that will be the optimal portfolio. And then if we read down on the axes, we can find what the expected return of that portfolio is and what the standard deviation of that portfolio is. Now the capital market line, this is a slight difference from the capital allocation line. Let's think of a portfolio of assets. It's actually a fictitious portfolio that is a valuated portfolio of all assets traded on the market. We're going to call this portfolio the market portfolio M. So M is going to denote that market portfolio. This would include not only any financial asset, but it would include any other type of non-financial asset, literally every asset that exists, and then a valuated portfolio of all those assets. So the capital allocation line that connects RF with portfolio M, which is the market portfolio, is specifically called the capital market line. So a capital allocation line could be could be a line that connects RF with any portfolio P. Pick any portfolio and you can have many capital allocation lines coming all out of RF. But only one of those lines is going to connect to the portfolio M, the market portfolio, and that is the capital market line. Now, as I said, we can't really observe the true market portfolio because many assets, we can't compute their value-weighted contribution to the portfolio. And so what we usually do is we use some type of proxy, which would be a well-diversified portfolio of many assets that are traded on the market. Typically, we use something like the S&P 500, which has 500 different assets and which is pretty broad, to proxy as a market portfolio. Now, just very briefly to finish up, passive and active strategies, this is a very important concept. A passive strategy means just buying a share of the market portfolio or the market proxy like the S&P 500 and holding it without taking any type of active role in trying to manage the various contributions of specific assets in that risky portfolio. So in that sense, because you're just buying and holding some broad index, it doesn't require any security analysis. An active strategy, on the other hand, is one that requires a lot of very individual security analysis, trying to understand what is underlying each asset in the portfolio, and then trying to take active strategies to increase the portfolio return by trading those individual assets in the risky portfolio.